Welcome to lesson 2 from chapter 3, functions, year 2 pure mathematics. Today we're going to look at 4 properties. We're going to look at mappings as a precursor to functions, functions themselves, and we're going to also look at aspects of functions that we call domain and range. So there's going to be lots of keywords today that you'll need to be aware of as we progress through the lesson. So there are 4 warm-up questions as usual. Please read the questions carefully, pause the video, and I'll go through the solutions with you. Okay, and let's have a look at question 1. All right, so we've got a definition to start us off, which is unusual for a question. So we have the definition of a mapping. So this is the antecedent of a function, essentially. So a mapping is a rule that matches a set of inputs, so another keyword there, which is interchangeable with objects. Okay, so an input or an object is the same thing. And the mapping will take your inputs or objects and transfer them to a set of outputs. So it's a rule that connects inputs with outputs. And another rule, in fact, I'll just highlight that in maybe a different color just to show that we're talking about a different property. So the inputs map to outputs and objects map to images. Okay. And a mapping, as it says here, can be described in words or through an equation. So you'll have done mappings probably in primary school. You'll be familiar with things like function machines and similar things to those. And an equation would be something like y equals x plus 1. So if you take this as an example that I've given you here and think of this as a mapping, what would happen is you would take your input, your x value, okay, and then we apply a rule, send it to the y value, and the rule that connects them is, of course, that you add 1 to each of the x values. Okay, so that's what a mapping does. It takes one set of numbers to another set of numbers via a rule. So what we have here is we have a box containing some inputs. So this would be a set of inputs, if you like. And remember, of course, you can replace the word inputs with objects. If that, just to make it, just to really embed those keywords. And your set of outputs we can also call images. It's the image of the object. Okay. Now, the variable that we use more commonly for inputs is, of course, x. Okay, and the variable we use for outputs is y. So you might know them as independent and dependent. So x is the independent variable in that we perhaps have some choice over what we put in to our rule, but y is a dependent variable because it depends on what the x input is. Okay, so the y is predetermined, if you like, by the x value. So that's why we have independent and dependent variables. And you'll know in mathematics we tend to plot the dependent variable vertically. Right, so we have the 2 boxes, inputs and outputs. We have to create an equation that matches, so create an equation that matches every input to an output. So don't worry if you didn't think of one or you couldn't see one. That's perfectly all right. It's just an exercise to see if we can actually create a rule. And there is a rule that exists. It's good to think of this as sequences, really. So for example, if I have my x inputs, if I just write them down like this, I've got 0, 1, and 2. So those are my inputs, and then my outputs. Well, if we have a look at the outputs, they're not necessarily in the correct order. You can't assume that. But what are we going to get? Well, if you look at the numbers, maybe if I just rearrange them, so if I put them in the order 1, 3, and 5, okay, because the inputs are in order, let's put the outputs in order. That would make sense. They seem to be increasing by by 2 each time. Okay, so perhaps there's some kind of nth term rule I can use here. So if I assume that 0 maps to the y value 1, so let's just assume that for starters, okay, and that 1 maps to 3, and that 2 maps to 5, and we know they're increasing by 2 each time. What is the rule connecting them? Well, so this is increasing by 2, and so is this. Well, it's going to be 2x, isn't it? And then there's going to be some kind of adjustment to be made. So if I double 0, of course I get 0, but if I add 1 to it, I get 1. If I double 1, as we can see here, I get 2, and then if I add 1 to that, I get 3, so that seems to work. And if I double 2, which is 4, and add 1, I get 5, which also seems to work. So I'm going to put my rule down as y is equal to 2x add 1. Okay, so that's the rule connecting my inputs to my outputs. And for part B, oh, there's a typo there. Sorry, that should be part B. I apologize. Draw arrows to show the matchings from each input to its correct output using your rule. So we just draw some arrows. So this is how you would have drawn a mapping back in probably primary school or year 7, something like that. So your arrows, so obviously 0 maps to 1, so I'll put an arrow that way. 1 would map to 3, and 2 would map to 5. So if you're interested in functions and things like this, this is what we would call a one-to-one function, because first of all the inputs map to one specific unique output, and it's also what we call an onto function, because every input maps to an output. So in mathematical terms, these are called injections and surjections and bijections. Okay, but you don't need to worry about that at this stage. Okay, so that's question 1. Now for question 2, we have 2 more boxes. We've got objects and images, and we're told to create an equation that matches every object. So maybe I should have stressed that a bit more. I'm going to stress it now. Every object in the objects box to an image in the images box. Okay. Now, can we think of a rule? Now, you might notice a problem initially, that we have more objects than we have images. So could this be a one-to-one mapping? Probably not. Okay, you're not going to have each object mapping to one unique image. That's not going to happen. Okay, but is it going to be onto? Are we going to use all those values in the images? Well, can we think of a rule? Well, we've got -1, 1, 2, and 0, and these numbers look quite familiar. Maybe if I'd added 3 to my objects, it might have been more clear. But if we look at those numbers, these to me look like square numbers. And indeed, if you take -1 and 1 and square them, they both map to 1, don't they? Okay, so I'll put the arrows on straight away. I'm thinking that this is going to be x squared. Okay, so -1 and 1 will both map to 1 if you square them. Okay, all right, and 0 of course maps to 0, and 2 would map to 4, so this seems to work. So 0 would map to 0 and 2 would map to 4. So I've actually done the question in reverse order, but it's okay. We were thinking aloud, weren't we, when we were doing this? So those are the individual mappings, and our rule that connects them, we're going to have the rule y is equal to x squared, just through inspection. Okay, so I hope that makes sense. So this is a different type of mapping. So this is not what you call a one-to-one mapping like you see in question 1, but it's a mapping nonetheless. Now for question 3, we have to do a bit of marking. We have a student was asked to sketch the graph of y is equal to the modulus of 2x subtract 1. And this is their sketch. And you're asked to use a coloured pen to correct it. So you're going to mark this sketch. So if we just try and sketch the graph ourselves, well, it looks like the shape is correct, doesn't it? It would be the graph of y equals 2x subtract 1. So it would have a y-intercept of -1, and then that would be reflected. So this would give us a y-intercept of 1 when we take the modulus. And indeed, you can check this. So we'll check the intercepts first of all. Okay. So if you're not seeing what the problem is immediately, there's a few things you can check here. But the shape of the graph seems to be okay, and there's no scales on the axes, so that would be acceptable. So the intercept. So when you have x equals 0, that of course will give us the y-intercept. So let's just check that. They've not labeled that, but we'll have a look at it anyway. So when x is 0, y would equal the modulus of 2 multiplied by 0, subtract 1, okay, which is going to be the modulus of -1. And -1, of course, would be the y-intercept had the modulus function not been applied. But because we take the modulus, that reflects in the x-axis, so that would be 1. So the y-intercept would be 1 on this diagram. In fact, I'll just label that in a different color. Okay, so this y-intercept would be 1, which isn't labeled, which they probably should have done. And now we can check the x-intercept. So this is when y equals 0. So when y equals 0, well, we have to solve the equation, when does 2x subtract 1 modulus equal 0? Well, there's two options to solve this equation. You can see from the diagram that it doesn't actually matter which equation you solve, either the positive branch of this, which I'll just label that in yellow, or the negative branch, which I'll just highlight in green. So if we take the positive branch first of all, we'd set up the equation simply 2x subtract 1 equals 0, which would give us x equals 1/2. So I think we've spotted our error straight away. So that would correspond to the yellow highlighted part of the graph. You could also do it using the negative branch, of course. So remember from the previous lesson, you would just negate the whole of that equation. So we'll take negative, and then it would be 2x subtract 1. Okay. And another way you can write this, of course, is if you don't like having the negative on the left-hand side, multiplying the 2x subtract 1, you could multiply all of that by -1 and make the actual constant value on the right-hand side also negative. So basically switching the negation from one side to the other. But we'll see in this case it doesn't make any difference because we have 0 on the right-hand side. So this is going to be -2x plus 1 is equal to 0. And this is, again, going to give us -2x is equal to -1. So x is equal to 1/2. So whichever equation you choose, be it the positive branch or the negative branch, I'll just highlight that to show you what I'm referencing, you're still going to get the same answer, which is x is equal to 1/2. So in a rather sort of labored, laborious way, which I've just done, we can see that the problem with the sketch is this labeling here. Okay, so that should clearly be 1/2. And you probably did that a lot faster than I did. So that's the correction, and they also should have labeled the y-intercept as well, in my opinion. So for part B, we have some more student work. The student was asked to solve this equation, and they did this response. Now, at first glance, you might think, well, they've not changed the sign of the equation, but as I've just stated, for the second equation, here, which would this would correspond to the negative branch of that graph. So I'll just be consistent with my negative branches and use green. There's nothing wrong with the first equation. You would set x subtract 3 equal to 4. That would be absolutely fine. In the negative branch, you would say, okay, well, you should take the negation of x subtract 3 and set that equal to 4. But you'll notice that that is the same thing as saying x subtract 3 is equal to negative 4. So the working out there seems to be okay. So what are our answers? Well, if we add 3 to both sides on the left, we do get 7. So I think that looks correct. And if we add 3 on the right-hand side equation, this is where the problem lies. Now, if we add 3 to both sides, we are not going to get negative 7. This is a sort of classic negative numbers problem here, isn't it, or a mistake? So the answer should in fact be negative 1. Okay, so those are the corrections. Okay, for question 4, we have a graph sketch to do. So we have a quadratic, x squared subtract 2x plus 3. We have to deduce and label turning point and any points of intersection with the coordinate axes. So let's just see what's going on here. We can see clearly just from the fact that we have a positive x squared coefficient that this is going to be a happy graph. So it's a positive. So what I mean is it's not like negative x squared or negative 2x squared. It's just positive. It's got a coefficient of 1, or a is 1, however you want to call it. So it's going to be that shape. So we know that much just by looking at it. We also know the y-intercept. So just by knowing how to read it, we can see that the plus 3 is going to give us a y-intercept of plus 3. The question is, does it have any intersections with the x-axis, and what is the minimum value? So clearly it's going to be a minimum point, so we just need to deduce where that is. So the first thing I'm going to do is I'm going to complete the square. So if we do that, we halve the x coefficient and put those in brackets. So it's going to be x subtract 1 all squared. And remember, of course, if you expand that, you would get x squared subtract 2x plus 1. Okay, the plus 1, I don't want that. I need to take that away. So I'm going to subtract 1 from here, and that will remove the plus 1 from there. So everything that I've just written down in that first row, so all this corresponds with the x squared subtract 2x. Now I need to add a 3 to create the equation. So I'm going to add 3 on the end, like so, and therefore I get the same equation. So just to tidy up those constants, this is going to be x subtract 1 all squared, and then that's going to be plus 2. Okay, so the implications of this are, again, if you know how to read what's going on, we have this value here and this value here will tell us everything we need to know about the minimum point. So if you reverse the sign of the negative 1 inside the bracket, this tells us that we have a minimum at coordinates 1, 2. So the y value of the minimum is at the point 2. So I can indicate that on my graph straight away. So at the point 1, which I'm just going to put on here on the sketch. So there's 1 and 2 on the y-axis. So this is where the minimum is going to go. And I can put my curve in now. So which color? I'll use blue for this. So the curve is going to go through like this, something like this. It's not my best effort, but it will do. And the y-intercept, of course, is going to be at 3, which we can see here. All right, so have we got everything on our checklist? So we've identified the turning point. We've done that. And the only point of intersection with the coordinate axes is the y-intercept. And you could also, if you weren't sure whether there were x-intercepts or not, you could use Well, completing the square will tell you that, because the minimum is obviously above the x-axis. So this value here 2 is greater than 0, so there's not going to be any roots whatsoever. But you could also use the discriminants. If you took the discriminant of this quadratic, and I'll leave it for you as an exercise if you're interested. So if you took the discriminants, you would see that the discriminant of this quadratic would be negative, which means there's no real roots. So quadratics are interesting in that they have lots of properties, and if you understand these properties and know how to read them, you can deduce anything you like about the curve. Okay, so that concludes the warm-up, and we're going to have a look at domain and range. So for the next section, we're going to take a closer look at some more familiar domains. And the task here is to look at these 4 examples and try and deduce what the range of values of y would be given the domain that is presented. So for the first example, we're going to look at the graph y equals x plus 1, and the domain is the entire real line. So take a moment to think about this, pause the video and try these 4 examples, and I will go through the solutions with you. Okay, so if we look at part E, the top left box, a good way to do this is to sketch the graph. So these are presented, although they're given the name functions, they're presented as graphs, aren't they? They're equations of, in this case, a straight line. So if we draw or sketch the graph, I'm just going to put some axes on here. And we'll do a little sketch and we'll try and deduce what's going on as is what's requested. So this is the x-axis, and we'll label that, and the y-axis. So there's nothing particularly scary about this graph. We'll just draw it as you've probably done so many times before. So we'll do this in green. So it's got a gradient of 1, and it's going to cut just above the origin at the point 1. So that's roughly what the graph looks like. So I'll just indicate that on there. So that's where the y-intercept is, and of course it's going to cut the x-axis at -1. So, and let's label the graph as well. Let's do this properly. So we can see that this is going to be valid for the whole real line. It doesn't matter what real number you choose, you can always add 1 to that value and generate a new real number. So if you look at how this graph is projected onto the y-axis, is there a y value that I can read off for every single x value I read off? So for instance, whatever x value I pick, it doesn't matter where it is, will I be able to read off some corresponding y value? And the answer is, of course, yes, isn't it? So we can see that whatever x value we choose, adding 1 to it means that we will always be able to generate a y value. So if the domain is the entire real line on the x-axis, then clearly the domain, sorry, I beg your pardon, the range, if you look at that, there is a y value for every single one of those x values. So the range is obviously going to be the entire real line as well. So we write it in this fashion. So we would say the y values would also be the entire real line, because that's how it's defined. So that's the first one. Now, if we move on to F, we have a quadratic, okay, very simple quadratic, y equals x squared. And again, this is defined for all real numbers. So again, draw the graph. Let's sketch it. So we'll put some axes on here. If you haven't done this, please do it now. It's a good idea to sketch the graph so you have a good idea of what's going on. And graph sketching is such a useful skill in this course. So we'll put that x-axis there, the y-axis there. And if we sketch the quadratic, I'll stick to this green color. So I'll draw this parabola on here like this. Okay, so something like that. And this is the graph y equals x squared. Now then, you can see no matter which x value we choose, Okay, I can choose any X value. That's a bit wonky. I can choose any X value and I'll be able to read off a Y value. Okay, and then there are places, of course, where if I read off a different X value, it will return the same Y value. Okay, but that doesn't matter. Okay, that's part of it being a many-to-one mapping. What we're interested in, of course, is the range of values of X that you're going to get. Well, this is where it's a bit more interesting, isn't it? So you can see that we can put in any X value we like. That's how it's described, the entire real line, and we square that number. Whatever the real number is, we square it and we generate a value in the range. So what are the Y values that we're going to get out? Well, you'll notice from the sketch that this graph has a minimum value, okay? And its minimum value occurs at the point 0, 0, okay? At the origin. And the minimum value means something, doesn't it? It means that the graph cannot exist below the x-axis. So the range is just going to be all positive real numbers and also equal to 0 as well, because if you put 0 in and square that, you're going to get 0. But there is no number that you can square that will generate a negative number, okay? Not in the real line in any case. So this function has a range. Y would be a real number, but there is a restriction such that Y is greater than or equal to 0. Okay, and our sketch confirms that. So I hope that makes some kind of sense. Now, moving on to G, we have a reciprocal function 1 over x. So once again, let's sketch this. These are standard functions we should know how to sketch. So I'll put that on there and I'll just move that slightly. Okay, so we sketch the graph. It's the two arcs, as you know. So, okay, and we have asymptotes on the x-axis and on the y-axis. So let's label those. Okay, so this is the graph y equals 1 over x. Now then, I've just gone hell for leather into that and arbitrarily just drawn the graph from memory. I know 1 over x is the two arcs in opposite quadrants, but what I've not paid attention to is the domain. Now notice the domain here. I've specified x values greater than 0. Now that's important. So that means that my domain is only allowed to be the positive direction on the x-axis. So that means that this part of the curve, I just have to erase that because that's not valid for my domain. And the question is, what y values will be returned once I put in these positive x values? Well, you can try some out. So if we pick any value, okay, it looks like we're going to be reading off some positive y values. And it looks as though that as the x values increase, the y values are going to become smaller and smaller. Now, if you look at the projection, and that's what, like a shadow cast by the function on the y-axis, as if you were shining a torch from right to left against the function, it would cast a shadow on the y-axis along here. And that's gives you a fairly intuitive picture of what the range is actually going to be. So it looks as though my range, from what I know about this function, is going to be y values that are greater than 0. Okay, they can't be equal to 0 because y equals 0 is an asymptote, but they can be greater than 0. Also notice, of course, that I'm not specified that y has to be a real number. It's not specified here in the domain. So again, I don't have to specify that in the range. It's implicit in the context of the question, what is meant. Okay, so I hope that makes sense. So all positive real numbers for the range for part G. And lastly, for part H, we have a quadratic. And you'll notice this is the one we looked at in the warm-up. Now, I've chosen this for a particular reason. And what I'm going to do, I'm going to complete the square. And I'll just write down what we found earlier. If we can complete the square, we're going to get x subtract 1 all squared plus 2. Now, why have I completed the square? Well, if we look at the graph again, we'll put the graph in as we've done for the other 3 cases. So we'll put that in, we'll just sketch the graph. We know that there is a minimum point at or with coordinates 1, 2. Okay, so I know that's the minimum point. I'll just make a note of that. So there's a minimum at the coordinates 1, 2. So if I just indicate that on here, so if that's 1, that's 2, there's my minimum, and I'll put the graph on. Oops, I've missed it. Something like that. Okay, and we have a y-intercept at 3. Okay, there we go. And I'll just label that. So this is y equals x squared subtract 2x plus 3. And there's no real restriction on this. It's the whole real line that we're interested in. So we can put in all real numbers, all real x values. It's valid for all of them. So we just have to deduce what are the y values that we're going to get out of this. Well, because we have a minimum, we've got our answer staring at us, haven't we? We know that the lowest value you can ever get is 2. So the projection of my graph onto the y-axis is going to be anything that is 2 or greater. And it's specified by this number here. So that's the range. The minimum is 2, so anything above 2 is valid. So we can now write down our range. So y would be a real number, however, such that there is a restriction, y is greater than or equal to 2. So this is another reason why completing the square is really useful. It's not just for solving equations, it's really useful for deducing the range of your quadratic. Okay, so I hope that makes some kind of sense. So now let's move on and do some more examples. All right, now we're just going to have a look at something called restricting the domain. And this is a really useful tool when we're working with functions. Now, in this instance, we've got a mapping the square root of x. So y equals the square root of x. And we've defined the domain as all real numbers. Now, you should be able to see from the graph also on the left-hand side here, if I allow all real numbers as inputs, we're going to have a problem, aren't we? Because it's only the positive real numbers and 0 that are defined for the mapping y equals the square root of x. So at the moment, this can't be a function because everything that is less than 0 on this side, all this stuff has nowhere to go. You cannot take the square root of a negative number and get a real answer. So there is a problem. So this is not a function. So we'll just make a note of that. So the mapping, y equals the square root of x such that, or where x is a real number, is not, and I'll underline that, it's not a function. Okay, it's not a function because the negative branch of the real line has nothing to map to. This would be what we call a partial mapping that I alluded to earlier. So it is a mapping, but a partial mapping. But can we make this into a function? Well, we can. Okay, we can make this into a function if we restrict the domain. So if we restrict the domain, I'll just remove that. Okay, if we restrict the domain simply to the positive real numbers and 0, then we don't have a problem. Every single element in that set, I'm drawing my wonky line again, maps to a particular y value. Okay, so it goes to some element in the range. So if we restrict that domain to just the positive real numbers, we're okay. So we're going to make a note of that. So we can restrict the domain. So in other words, put some conditions on the domain. Such that the mapping y equals the square root of x is a function. Okay, and we'll just write down that restriction now. So i.e., we take y equals the square root of x, where or such that x is a real number, but or such that x is only positive or 0. Okay, so we've restricted our domain. So I hope that's clear. And this is a like I say, a useful tool, because you might have a situation where you have a mapping and you want it to become a function because functions have particular properties. And you can do that by being very careful and making adjustments to the inputs. Okay, so the next thing you're going to do is you have a task. So we're on sections I and J, keeping this alphabetical system going. And what I'd like you to do first with these two mappings, so we have the first mapping is y equals 1 over x squared, as you can see here. So, and I've got a domain of all real numbers. And the second mapping is y equals the square root of x subtract 1. And again, I've suggested all real numbers there. So they're mappings. Okay, they could be partial mappings or full mappings, we don't know. But I would like you to make those into functions by restricting the domain. And you can do this by sketching the graph. If you can sketch the graph, it will reveal the answers very, very quickly. So please pause the video and try those restrictions, restrictions of the domain. Okay, and let's have a look what the solutions might be. So that you could have come up with a different solution to what I'm coming up with now, but we'll have a look. So I'm going to sketch the graph of 1 over x squared, and this is probably a standard function. I'm just going to sketch it here in the corner. So put the axes on here. We'll just do this really, really quickly. So 1 over x squared, it's like 1 over x, of course, but because we're squaring x, it's going to make everything positive. So it's going to look something more like that. So that's my sketch. So y is equal to 1 over x squared. And if we're considering the domain, at the moment, I'm allowing for all real numbers. Now, immediately, you should see a problem with this. Okay, and I should label my axes. Let's do this properly. So there's the x-axis and there's the y-axis. So you should see a problem with this. Are there any x values that you cannot input? Well, just look for the asymptote. There is a vertical asymptote at x equals 0. Okay, so the y-axis. So this is an asymptote there. So that means that you cannot input 0 because you'll be dividing by 0. That would class as a restriction. As soon as I remove the element 0 from the domain, every single element in my domain now has somewhere to go. I can square any number, any real number, and reciprocate it, and I get a y value. Anything apart from 0. Now, you might have tried a different kind of restriction. So another restriction you could have done would have been perhaps just restricting to the positive real numbers. You could restrict that, so that would be another option. And that would have obviously avoid using 0. So you could just take all the positive numbers, excluding 0, of course. That would be absolutely fine. And if you did that, then you would just dispense with that part of the curve. Or you could take just the negative real numbers. And these are still infinite sets, of course. Okay, as long as you exclude 0 from your domain, it will be a function. Okay, now if we move on to J, we have a transformation of the graph from the restricting the domain example above. So if you notice, it's a translation. It's going to be the graph shifted 1 unit to the right. Okay, so let's have a think about what this would look like. Let's sketch it. I'll put it just here, like so, and we'll put the x-axis on as well, and let's label our axes. There we go. So x and y, and there's the origin. So if you look at this, are there any x values that we can't put in? Well, we cannot take the square roots of negative numbers. We know that, and get a real number back. Okay, if you're doing further maths, you'd probably be able to do that. So we know that x subtract 1 must be greater than or equal to 0. Yeah, that's the condition. Okay, and you can tell that from this square root. And what does that imply? Well, that means that x must be greater than or equal to 1. Okay, which also is indicative of the transformation. The graph that I haven't sketched, of course, is here. So it's going to go something like that. So this would be y equals the square root of x subtract 1. Okay, and it's going to have an intercept at 1. So it's the shift of the graph above 1 unit to the right. So at the moment, the domain all real numbers is clearly not possible. But by solving this little equation, just by recognizing the fact that you can't take the square roots of negative numbers, it gives you a restriction. So lo and behold, we've now got our restricted domain. So as long as x is greater than or equal to 1, this is going to work. Okay, and again, you might have chosen something else, but anything greater than or equal to 1 has a y value corresponding. Now we're going to move on to the actual worked examples. So you've had a look at mappings, functions, how domain and range operate. So let's put them into practice. All right, so we're on to the worked examples, and we're going to look at types of mapping here. And you've got 4 diagrams, and the task is to match each diagram to one of the mappings below. So this is just a review of what we talked about earlier. So if we look at the first diagram, you can see that for our inputs, which we also call objects, which we can't necessarily call the domain because we don't know if it's a function or not, but you can see that for each of these inputs, we seem to be going to 2 images. Okay, so 2 outputs. So if we just write down what this actually means before we try and match it. So this means that one input is going to match to many outputs. So this is a one-to-many mapping. And remember, if you have had one-to-many, you can't function. Okay, so there we go. So we can see that this matches to the one-to-many category. Okay, the second one, we have a straight line graph, and as you know, when you put in an X input on a straight line, you perform some kind of rule, and you always generate a single unique Y value. Okay, so this is what we call a one-to-one mapping. So one unique X input will be sent to one unique Y output. So straight line graphs are one-to-one. We'll do more about one-to-one later in the chapter. They're quite important. The third diagram, we have 1 over x, and we've just been looking at 1 over x. 1 over x would need a restricted domain to make it a function, but as a mapping, we don't need to do that. We just have to decide what kind of mapping it is. So if we just have a look at maybe a couple of points here. So if I take a point here and match it, it's going to go to one particular Y value. Okay, or I could take an X value over here. That also is going to go to one particular Y value. It's simply just the reciprocal of whatever the X value is. Okay, so this is also one-to-one. So we'll match that as well. So this is going to match to one-to-one. And the final diagram, we have a quadratic x squared subtract 1. And the diagram basically gives us the answer, doesn't it? If we take more than one x input, as you can see here, so we have x, whatever that is, and negative x, just highlighting those, they in a quadratic, they can go to the same y value. So in other words, to generalize that, that means many inputs map to just one output. So that's a many to one. That's what quadratics are. So many to one would map here. Okay, and then you might want to decide which of these are functions. So that's what part 2 of this question is about. Well, I've already said it. If it's one to many, you can't function. Okay, so all the ones that are functions potentially are the one-to-one mappings. Okay, we can't have one to many, or the many-to-one mappings. A many-to-many mapping is a combination of a one-to-many and a many-to-one. Either way, that's not going to be a function. Okay, that would just look like chaos on the screen completely. So which of these mappings are functions? Well, the one-to-many one, we can disregard that one. So let's just make a note. So this is not a function. Because of the type of mapping that it is. Okay. The straight line graph, if you took a domain for all real numbers or a restriction, it doesn't matter. This is a function. It's a one-to-one mapping. So that's definitely a function. Diagram 3, or the third one, would be a function if we restricted the domain. So if x was not allowed to be 0, then it would be a function. Okay, so you'd have to restrict the domain to ensure that the elements, the inputs, have somewhere to go. Okay, and the many-to-one. Okay, well, if we again look at this, this would be valid for all real numbers as well. So there wouldn't be a problem with this. We could restrict the domain or pick out certain values. There's no limit really with that. So the last one, of course, the many-to-one, is a function as well. Okay. So you can take any real number, it doesn't matter, square it and subtract 1, you'll generate another real number without any problems. Okay, so that's worked example. Moving on to worked example 2, we have a function defined as 2x subtract 3, only for this small finite set of x values given here. So it's a good idea just to list those x values. There are inputs for our function. So we'll write a list of x vertically. So 1, 2, 3, and 4. So those are the elements of the set, if you like. And the image, the y values that we get out of it, we get by applying the rule that's been provided. So the function is 2x subtract 3. So you take any of those x inputs, multiply them by 2, and then subtract 3. So what's going to happen to 1 if we do that? Well, if we double 1 and subtract 3, of course, we're going to get a negative 1. And this is the same as a sequence, isn't it? It's a linear sequence where x would be your n and 2x subtract 3 would be like your nth term. So it's going to increase by 2 each time. So we're going to have 1, 3, and 5. And you can just check that using the position to term rule, can't you, which is the function itself. So if we double 2, as you can see here, if we double 2 and subtract 3, we do indeed get 1. Okay, so it appears to work. So this is our function, and it's a good idea just to draw the mappings on as well. So this just goes straight across. So 1 goes to 1, 2 go, sorry, I beg your pardon, 1 goes to negative 1, 2 goes to 1, 3 goes to 3, and 4 goes to 5. So this will help us for the next part of the question. And what we need to do is state the range. Now, the range is also a finite set, and it's just a collection of all the objects in the image of our functions. It's the collection of these objects here. So we'll write them as a finite set as the domain was given. So y would be an element. This is our image of the set containing negative 1, 1, 3, and 5. And we also have to state what kind of mapping this is. Okay, so it is a function. We know it's a function, but it has to be either a one-to-one mapping or a many-to-one mapping. Well, clearly, each element in our inputs is mapped to one distinct element in the output. Okay, it is one-to-one. So we'll just state that as well. So this is a one-to-one mapping. As all straight line graphs are. Okay. Right. So that's part A. Now moving on to part B, we've got a slightly more complex function. We have a set of real numbers for our domain, but it is restricted. It's restricted across an interval between 0 and 5 inclusive. And the rule that connects our inputs to our outputs, which we're going to have to find, is the rule x squared subtract 4x plus 7. So what could we do with this? A good idea, of course, in situations like this is to sketch the graph. Okay, we could have sketched the graph in the first function, but because we're putting in a finite set of elements, you can actually work them out individually. All right, that's not an issue. But here we're looking at intervals on the real line. So let's just examine more closely some of the properties of our function g of x. Well, we can see straight away we've got the y-intercept, which is plus 7. We can see that just by looking at it. We also know from the sign of the x squared term, this is a positive x squared term here. So that tells me that this is a happy, in inverted commas, quadratic graph. So it's going to be that shape. And we can also discern a few of the properties by doing some algebraic manipulation. So we can just maybe complete the square. So let's do that. So if I complete the square on this, I'm going to halve the x coefficient and square the bracket. And let's just examine what that would give us. We would get x squared subtract 4x plus 4. Okay, so I don't want the plus 4, so I'm going to have to subtract that 4. So if I subtract the 4, I can then just ignore that bit. Okay, so what I've just written down in completed squared form is exactly the same as this. So we've constructed the first two terms of the quadratic. All we need to do now is add 7. Okay. And that will give us the exact same expression. And notice we can just collect the negative 4 and the 7 together. So that's going to be x subtract 2 all squared plus 3. Okay, so more important information here, if you know how to read it. We have the coordinates of our minimum point. Okay, we know it's a minimum because it's a smiley graph. So it looks like there is a minimum at the point 2, 3. So that's very important. Write that down. Okay, so we're just going through all the key properties of quadratics here. We notice that the minimum value is greater than 0, so there's not going to be any x-intercepts at all, and you'd be able to tell that from the discriminant. But we don't need to do that. Okay, we've got enough information now. But what I'm doing is I'm just going through the properties as if I had x inputs that would cover the entire real line, as you can see here. But that's not what we have. Okay, we have a restriction. We're restricted between 0 and 5. So what do we need to consider? Well, we're only going from x equals 0 to x equals 5. Now, we know what happens when x equals 0. Okay, when x equals 0, we get the y-intercept, so we know that y would equal 7, okay? But what would happen when, or I'll put g of x, in fact, seeing as we're talking about the function g, so I'll just change that to g of x. So g of x, which plotted on a graph, y equals g of x, would be y equals 7, of course. So what happens when x equals 5? Well, when x equals 5, we put 5 in, g of 5, and I've not also noticed maybe I should put g of 0 in there as well. Oops. So g of 0. Yeah, and g of 5, well, if we put 5 in, using the completed squared form, we would have 5 subtract 2. Put it over here. 5 subtract 2, which equals 3. Square that is 9. Plus 3 is 12. Okay. Now, let's have a go at drawing the graph. So I'll put some axes on here. We've got enough space, I think. All right, so I'm just conscious my minimum value is at 2, 3. So I'm going to put the curve. It starts at 0, of course, as well. So I don't have to worry about any parts of the curve that exist prior to that, although you might just want to draw it first and then just focus on the interval that you're interested in. So we're going from 0 to 5. Now I'm going to draw the curve first. So it's going to cut at 7. It's got a minimum at 2, 3. So let's see if we can get this right. So it's maybe going to do something like that. Okay, I've done my best with that. So let's just label everything. So this point over here is when x equals 5. Okay, we have x equals 0 already labeled. We have a y-intercept at 7. There, so y equals 7. We have a minimum point, okay, which occurs when x equals 2. And y equals 3. So that's also very important. You might just want to indicate that maybe with some dots or some lines just to show that you're reading off the point 2, 3. And also we have the coordinates at 5, 12, which is the final value in this set of ordered pairs. Okay, so I'll put it about here. So it's going to be about here. Okay, and if I read it off, that's going to be where 12 is. Okay, so again, you just might want to show that you're just reading that off. Okay, and this is the graph, labeling the graph, of course. Y equals x squared, subtract 4x plus 7. So we've got everything we need. Now, we're only focusing on this small interval, as I've said. So what are the y outputs that we get? Now, a naive approach, of course, if you don't draw the graph, you can fall into a trap here. Okay, and this is why I've sketched it. I've spent all this time explaining it. If you go in naively and think, okay, well, look at the x inputs. Well, if I work out the corresponding y outputs, okay, if I put 0 in, my y output for 0 would give me 7, as we've discovered, and my y output when I put in 5 would be 12. Okay, so that would imply that perhaps the range would be between 7 and 12. Okay, but if you did that, you'd be wrong, as we can see from the graph. You're assuming, if you do that, that the graph is what we call monotonic. You don't need to know that word, but it means it's either increasing or decreasing over an interval. Okay, and it's not doing that. We have the graph to prove it. So, well, that's not the way to do this, and that's a kind of a lazy approach. What we need to do is sketch it and look carefully at what the range is actually going to be. So from our diagram, we can see for that interval, the y values we get out start at 3 and go all the way up to 12, because we have that minimum value when y equals 3 and when x equals 2. So I hope you can see that. Just imagine you're casting a shadow, shining a torch onto the graph from the right to the left, and it's casting a shadow on the y-axis. Okay, so that's the range of values. So let's write that down now. So the range of G is y would be any real number such that it's between and including 3 and 12. All right, and we also have to state whether this is a one-to-one or a many-to-one function. Well, let's look carefully. Let's pick a point which will illustrate what we're trying to show. If it's a many-to-one, you can tell just by reading off in reverse. If I pick some y value between 3 and 7, as you can see here, all right, clearly, if I read off from x to y, so if I put the arrows going that way, you can see that we have two distinct x values that go to the same y value. So this is what we would call a many-to-one mapping. So this is a many-to-one. I forgot to put the hyphen in. Many-to-one mapping. And the quadratic curve without restriction is many-to-one, but if you restrict the domain, you can make it a one-to-one, and that's something we're going to look at in future lessons. Okay, so that concludes worked example 2. Okay, and we're on example 3 now, the final example from this lesson. And we have an unusual looking function here. This is what we call a piecewise function, which has two different rules depending on which section of the real line we're looking at. So it's defined as 3 subtract x, which is a straight line graph, for x strictly less than -1. Well, that's really important. And the second branch is defined as x squared plus 1, and that's for x greater than or equal to -1. Okay, so we've accounted for the entire real line there, but we have two different rules operating. And the changeover is at the point where x equals -1. So we're going to have to sketch this, and it's a good idea to examine what is going on for both of these rules at the point x equals -1. So I'll just label that point on our graph here. So we'll put it about here for -1 on the x-axis. So that's a point of interest. And let's see what happens. So if I sub in -1 into these rules, well, we're going to have 3 subtract -1. Okay, so subbing that value in. So just to make that clear. And that's obviously going to be 3 plus 1, which is 4. Okay. Notice though, I'm saying I'm subbing it in. It's not a valid point. Okay, it's not actually part of the function because -1 is not included. As you can see, it has to be strictly less than -1. So I'm just using that just with an air of caution here. So that point is not included. The point that is included is if I sub in -1 into the second function here. Okay, so into this, because you can see that -1 is included right there. So let's sub that in. So we're going to have -1 squared plus 1, which is going to be 1 plus 1, which equals 2. So that is a point on the curve. Let's put it on our diagram. So at -1, the y value on our function would be 2. So I'll put that somewhere about here. Okay, and it's going to be about there, that point. So that's a point on the curve. So what I should do is, because I know there's a disjoin, and when I say a disjoin, it means this is not continuous because these two values are completely different. Okay, if this was a seamless transition between from one rule to another, we should get the same value, but we don't. So this is a discontinuity. So I'm going to show that this point here is included by shading it in with a filled in black dot. And we're also aware that for the first rule, the 3 subtract x, if I put in 4, that is not a point on the curve. So I'm just going to indicate that on my diagram by putting a hollow circle, okay, to show that that point is not included. But we've accounted for the discontinuity on our diagram already. So what's happening for the rest of the rule? So we'll focus on the quadratic part first, i.e. this rule here. So it behaves as x squared plus 1 for the rest of the real line. So if I'm considering that all x values greater than or equal to -1, so that's all this, I just basically sketch the graph x squared plus 1. So that has a y-intercept at 1, and it's a quadratic, so it's a parabola. So I'm just going to draw this, make sure I'm not on highlighter mode. So if I come down like this, try and draw this, it's going to go through 1, and then it's just going to go up something like that. All right. Okay, and we'll just indicate that y-intercept. So that's at the point 1 here. Okay, so that branch, this is the graph y equals x squared plus 1, okay, for that branch. Now, for the first branch, so this is the 3 subtract x, this is a straight line. So looking carefully at this, what have we got? Well, we have a minus x, so that suggests a gradient of -1. So I'll just make a note of that. So we know m is -1. And the y-intercept, c, is equal to 3. So that means that if the graph continued, there would be a y-intercept here at 3, and it would be sloping down with a gradient of -1. So I can put that graph on there. I can just imagine it's continuing through past 3, so it's going to go something like that. Okay, so that branch, this is y is equal to 3 subtract x. All right, so we put all those different things together, and we now have a piecewise function with a discontinuity where x equals -1. And you'll notice that the 3 subtract x will now be valid for all x values strictly less than -1. Okay, so we'll just label this function as a whole now. So I've labeled the 2 branches, but the function, this is y equals f of x for the whole thing. Okay, and once again, just be aware that notation, if you don't like it, it's just the same as saying f of x is equal to. It's just a different way of writing it. All right. So I hope that's clear. So we've got our sketch done, and now we've got our sketch. We have an equation to solve. So we have to solve the equation f of x equals 6. Well, if we do that, probably this will be in the way, actually. I'm just going to move this label down. So if I'm considering the point f of x equals 6, that would be a straight horizontal line, wouldn't it, going across? So I'll just put that on about here, perhaps. Something like that. So we'll call that the line y equals 6. I mean, it doesn't have to be perfect, just has to be reasonably accurate. So that's the line y equals 6. And I've just removed my label. I forgot to put that back on. So this is going to be y equals 3 minus x for that branch. And if I read off, well, what we're going to get two possible answers. You can see that the line y equals 6 crosses our graph, our strange looking function, at two distinct points here and here. So I need to read those values off. All right, so what does that give me? Well, let's have a look. So it's going to come down like this. There's going to be a value there, somewhere less than -1, and there's going to be a value here, at some point greater than 0. So our job now is to find out what those points are. And it's the same kind of idea as when we're working with modulus graphs. You have to have a good idea of what the graph looks like in your head, and then you know which equations to solve. So let's just do a bit of algebra now. So if we're going to, so for solving, this is for part B, for solving f of x equals 6, this is what we're going to have to do. We're going to have to solve the equation 3 subtract x is equal to 6, first of all. Okay, that's to cover this point of intersection here. Okay, so I'll label that point A. Okay, and this is for point A. This will solve that, the x coordinate for that one. And for point B over here, we have to solve the equation where the second branch intersects the line y equals 6. So that's going to be x squared plus 1 equals 6, like so. So we solve them separately. Now, the first one is relatively straightforward, I think. So if we solve that, we're just going to get -x is equal to 6 subtract 3, which is of course 3, which means that x would equal -3. As confirmed by the diagram, it might not the best scale, but it looks like this is going to be a negative value, just somewhere less than -1. So that looks okay. So we've got that one. That's our first solution. And for the second solution, we have to solve a quadratic. Now, please take care with this, and you'll see why in a second. So to solve the second one, we're going to have x squared is going to equal 5. Now, if you know about solving quadratics, if we take the square root, we know we have two possible answers. So therefore, x is equal to the square root of 5, or x is equal to the negative square root of 5. Why do we have two answers when we clearly only have one? Well, when you solve an equation like that, you're assuming that you're dealing with the whole real line and you can accept all solutions. Remember that this is only valid when x is greater than or equal to -1. Okay, I'm going to put that in a bubble and highlight it because it's so important. It's only valid, that graph, x squared plus 1, is only valid when x is greater than or equal to -1, as you can see. So which one are we going to accept? Well, the only one we can accept is this one, because the second answer, the square root of 5 negated, is going to be less than -1. Okay, so we disregard that. So our two solutions are as follows. So we're going to get x is equal to -3, and x is equal to root 5. And those are the two solutions. Okay, so that concludes the worked examples.